Boris starts talking now about convection in plane layers.
So first, sorry for my English, huh? And then I will speak a little bit about convection in plane layers with the pencil code. That's the work I'm doing with Axel. And first, I will show you. So I'm from Toulouse, and Toulouse is here in France.
You get out. Google Earth.
And in Toulouse we have an observatory. The observatory is here in the mountains, just near town. And the observatory, maybe you know this observatory by name, the Pic-du-Midi Observatory. It's 1,900 meters. And here we have a big telescope, big 2 meter telescope. And sometimes I observe on this telescope spectropolarimetry.
What does it mean in French? Moon? Peak? What does it mean?
Peak.
Du Midi.
Peak du Midi. Peak because it's a high mountain, and du Midi is the name of the mountain. So that's the Pic du Midi mountain. Okay. And there are a lot of telescopes. This one and this one is 1 meter, which is the American, the US paid the mirror for the Apollo mission. Because actually, this telescope is making one of the best pictures of the moon. So the Americans paid us the mirror of this one.
It was in the early 60s or what? Early 60s.
Yes, in 62 and 63, something like that. So why we are interested in stellar convection with Axel? It is because we want to study the internal gravity wave excitation by fluids, convective fluids. Because we know that by heliosysmic convection that the solar core rotates almost with a solid body rotation. That means that here we have the convection zone, here we have it's the center of the sun, and you see that the angular velocity remains constant in the core of the sun. And then one way to get that is to have internal gravity wave, which distributes the angular momentum. Okay. So one explanation is internal gravity wave transport of angular momentum. The other problem is what we call the lithium dip problem in solar tip star. Here is abundance of lithium, okay, and here the effective temperature of the star. And you see that for some temperature around 6,500 Kelvin, there is a dip, okay? And the left border of the dip is well understood, actually. It's just transported by meridional circulation. But the right part of the dip is not well understood because one needs some physical process which kills the meridional circulation. And this process is certainly related to internal waves also. And then the problem is, okay, we know that certainly internal waves are responsible for the solid body rotation of the solar core and also of the right border of the lithium dip, but the problem is to excite those waves. And one excitation mechanism is by convective fluids.
I mean, is it fair to say that this is actually one of the contenders among magnetic fields on the other hand, but also anisotropic viscosity?
Yeah, that's true.
All of these three agents are possibly responsible for causing the tachocline exit.
Yeah,
what
but
it is.
There is some problem, for example, with the magnetic.
So you don't buy that?
Yeah, magnetic because of Ferrero law and so on. So I don't say that it is the only possible mechanism. It's one. So why we have wave excitation? Because we have penetrative convection. So it means that here it's a convection zone and here the radiation zone. And between the two zones, there is an interface. And here's the convective block, okay, which powers down. And normally, using mixing lamp theory, the velocity of the block is related to the, so this one is correct, it's not MLT. This one says that the velocity of the block is simply related to the contrast, temperature contrast between the block and the surrounding medium. And the MLT mixing lamp theory says that the temperature difference is proportional to the superadiabatic gradient. Okay, and then normally, when in the convection zone, of course, the gradient is superadiabatic, and the radiative zone is stable, so the gradient is subadiabatic. And this interface corresponds to the Schwarzschild criterion. The gradient is just adiabatic. And normally, in the MLT framework, the block stops here, because temperature difference between equal to 0 and then the velocity also equal to 0. So normally, in the MLT framework, the block should stop, and there is no penetration. Okay? But the MLT theory is based on acceleration forces. And when we put to 0 forces, it does not mean that it means that the acceleration is 0, but not velocity. And by inertia, in fact, the block penetrates in the stratified zone. Okay? And once the block penetrates, the Archimedes force reverses, and the block is break by the Archimedes force. Okay? And finally, when the block is break, it can transfer its kinetic energy to the medium by waves. Okay? So that's how we can excite internal waves. And one guy, maybe you know this guy is called Dan, made the theory of this penetration in 91, and he showed that there is two zones. One zone, here's the bed, okay, here's the bottom of the convection zone, and here we penetrate in the radiative zone, okay? And here's the convective flux and the radiative flux. And in fact, the block penetrates first, what is called penetration, until some distance where its Peckel number becomes unity. And when its Peckel number becomes unity, the block thermalizes with the surrounding, and we get overshoot. Okay? So there are in fact two zones. The first one is called penetrative penetration, where the Peckel number of the block is very high, and once the Peckel number becomes unity, the block is just a thermal adjustment layer, and it's the overshoot. And then gave a rough estimate of the total extent, it means penetration plus overshoot, and it shows that this shoot scale has the RMS velocity at the bottom power 3/2. Okay, so that's the theory.
Sorry, what was what velocity?
The velocity is the RMS velocity of the tube at the bottom. Okay, and normally the extent shoot scale has this one. That's the theory. But okay, now let me speak about stellar convection. So we are interested in a star like this one. The mass are less than 2 solar masses, because above 2 solar masses we don't have surface convection zone, but convective core. Okay? And the convection is like Reynolds-like convection, okay, except that the Reynolds number is very high. It's not really because the viscosity, the mean viscosity of the solar convection zone is around 10 to 2. It's like honey. That's the problem, that we have a very big convection zone, very big, astrophysical one. Okay? And we can calculate also the turnover time of the convection. And for the sun, it means at the surface it's around a minute, okay? And at the bottom of the convection zone it's around a month. Okay? And of course we have turbulence in the stellar convection zone. And if we put some numbers, we get that. Then for the Reynolds numbers, it's 10 to 13 at the top of the convection zone, and 10 to 10 at the bottom. For the radiative conductivity, we have a Prama's law, and we have a jump of about 100. The Peckley number, which is very important, is the 1000 at the top to 10 to 7 at the bottom. And the Prandtl number is very small. It's 10 to minus 10, 10 to minus 3. And this is what is called the thermal timescale problem. Because the thermal timescale of the convection is related to the turnover, which is the dynamical timescale, by the Peckley number. Okay? And because the Peckley number is very high in the depth layers, the thermal timescale becomes very large. Okay? So here, the thermal timescale is around 10 to 13 at the base, at the bottom of the convection zone. Okay? And then it means that any perturbation, thermal perturbation, will take time much longer than the dynamical timescale of the simulation. Okay? And then we have a problem because the dynamical timescale is the timescale of the simulation, for example, threefold timescale, for example. But we have below the convection zone, we have a radiative zone. And to relax thermally this radiative zone, we need to wait a lot of time. And then one solution of this problem is to start the simulation using mixing length theory setup. Which means that that's what I coded in the pencil code. Then it means that we say that the gradient is simply the adiabatic gradient plus some additional term which is related to the convective flux. Okay? So here two cases. The first case, I started the simulation by using the assumption that the entropy profile, the entropy grid, the stratification is adiabatic in the convection zone. Okay? So here the radiative zone and here is convection zone. And you see that the finite solution is there. And I need to go from here to here during the run. So I'm far from the final solution. And if I use the mixing length setup, now the solution, the initial solution is there. Okay? And you see that I'm not so far from the final solutions. Then I won a lot of time step. Then I won a lot of time step towards the relaxation of the convection zone. Okay? So that's a very good point for this problem. We can win a lot of time step by starting from almost relaxed solution. Okay? So now in the pencil code, you can have mixing length stratification in the start plus in phi, and it computes the mixing length solution of your problem.
The right-hand one will limit the diffusive time step less, right? The right-hand one will limit the diffusive time step.
Yes, we still have the time step limitation by diffusion, but we won a lot.
But it'll be not as bad because the second derivative's much softer. Right?
And then now for our problem, we need to have high Peckley numbers. Because in theory, we have penetration only if the Peckley number is very high. Okay? And then in the pencil code, what is coded actually is the polytropic models. Okay? And in polytropic models, the temperature gradient is simply related to the inverse of the polytropic index, and the radiative conductivity is also related to the polytropic index. And then now, since I'm using the pencil code, September last year, I tried to get simulation with large values of Peckley numbers. And the problem is that in the past we used one way to get strong convection is to decrease the radiative conductivity. But if we do that, decrease the radiative conductivity by taking negative value of polytropic index, we get a very big key jump, radiative diffusivity. And that's what we did in the past that simulation of using the pencil code, you see the fluxes. So not very well then. The total fluxes is there, the solid line. Okay, the radiative flux here, and the convective flux is this one, and the kinetic flux is this one. Okay, so that's the depth, and then the convection zone is there, and the radiative zone is there. Okay. And I took negative value, the polytropic index, and then a large convective flux. And if I look the relation between the convective flux and the RMS velocity, the slope is 1/3, and it's not correct. It's not correct because normally the square of the RMS velocity should scale as 2/3. And then if I'm looking the profile, the vertical profile of the RMS velocity, we see that the velocity goes to 0 very rapidly at the bottom of the convection, and then we get overshoot. Simply overshoot. The Beckler number tends to unity very rapidly here. It is because we have a strong difference between the radiative diffusivity between the two layers, because we have negative value for the polytropic index there, and then there is small value of K. The K is very small and K is very large, and then the block experiences a very strong jump. So that's not correct. And then finally we found the solution this year by starting using positive value of polytropic index, but we playing with the density jump across the convection zone, which means that we have large value of the radiative diffusivity in the convection zone. Of course, the polytropic index is less than the adiabatic one, but we play with the density jump across the zone by playing with the some speed at the top of the box. And then now things are very good, because now we get the good relation, scaling relation with the MHC. It means that the slope now is 2/3 as done by MHC theory. And now we get large value for the Beckler number at the bottom of the convection zone. Around now we get the maximum is 400, and now we are able to find the penetration region. It means that here you see the RMS velocity with depth here, and then here we have overshoot. You see that the RMS velocity tends to 0 rapidly, and here what do you see? That the RMS velocity now tends to 0, but not very rapidly. We have the penetration region. Okay, and then in this case, the Beckler number is around 400. And then first we have the penetration, and after that overshoot. And then also predict later on the slope of the stability parameters, the penetration versus the stability parameters. The stability parameters is simply related to the ratio between polytropic indexes, okay, between the stable zone and the convective zone. Okay? And that shows that in the overshoot regime, normally the slope should be, the penetration scale has S power to 1 minus 1/4. And if one has overshoot penetration, normally it's simply minus 1. And now we show that this theory is correct, because now we are able to get this regime, which is not the case in the past for people, in fact. And now, what's about the gravity wave excitation? So that's a result we published with Axel and Hauke and Bob last year, using Hauke's code. Last year I used it with Hauke's code. And we showed that, okay, so that's fluids. Here is convective zone, and here is radiative zone. So that's a result coming from Hauke's code. And then the plume go down, penetrate, and excite waves here. And here you see a big roll, which here is the roll, the signature of internal wave propagation. Okay, that's internal wave propagation there. Okay. And what we show here is that when the plumes penetrate in the radiative zone, the plumes can destroy the mold. You see the mold here, the walls disappear here. Which means that the wall has been destroyed, the mold has been destroyed by the plumes. So plumes can excite waves, but also plumes can kill waves. So that's two things. And by taking time frequency diagram of some projection coefficient, I will not go into detail here, we can find the times when the waves are excited by projecting on the eigenmode, the anelastic eigenmode of the source, the wave system. And we show that the lifetime of the mode, so this is the lifetime of the wave event, the PDF, the lifetime wavelength, and we show that the PDF peak around 2. It means that the mode lifetime, the mid-mode lifetime is around twice a period. So that's a good result, an important result. And now I try to do exactly the same job with a pencil code. And I can show you, for example, one simulation. So this one. So that's a snapshot of the entropy. Okay. For very long, maybe I should look. So here's convection zone, okay, and here the radiative zone. And plumes penetrate. Normally, how do you call it? Loops. That's right. It's minus loop, huh? No. What is
space north? I think afterwards. Let's put minus loop space north. No or not?
Minus loop. Note. And then normally the plumes stop here, but you see that they penetrate. And what you can see here, it's characteristics of the waves, of the internal waves. You see some straight lines, some lines. And that line corresponds to the characteristic of the hyperbolic operator of the waves. Okay? And then that simulation using pencil code. And what I did also, I'm coming from in Toulouse. We are our specialty is oscillation, stellar oscillation, and stellar oscillation. As I said yesterday to Tony, generalized eigenvalue problem. It means that eigenvalue problem. Our specialty is eigenvalue problem with rotation. That means that computing the eigenmode of the rapidly rotating stars, and by adding the Coriolis force and computing the mode of the eigenvalue of infinite coupled system of coupled equations. And then during my PhD, my thesis, I made some interface to compute using the idea, this ideal interface, saying that we get some muon kinetic energy, spectra, the velocity field, and so on, and we get an axis file, and we compute everything using Fortran, and then we plot. Okay, and I did the same with a pencil code with an interface with iPen. So it's still a prototype. Huh? So you see, you give the path of the simulation, and you can compute first the setup of the simulation. It means, for example, it's a monoprocessor job, the resolution, the size, so it's a 2D job. But you can also have parallel job and compute on the same. So the polytropic index of the job, the jump, density jump, the flux, and code at the bottom, the density and the Rayleigh number, the corresponding Rayleigh number. Okay? And first, you want entropy of the entropy of the last snapshot of the entropy and the mean vertical profile. You want the fluxes, hop, get the fluxes. Fluxes.
Wow.
Okay.
That's not time averaged now, right?
Mm-hmm.
It's not time averaged.
Yes, of course.
It's time averaged.
Yeah. The fluxes for the For here you specify the number of bar files you want to take.
Oh, okay.
Okay, so I have 500 bar files, and I take the last.
I mean, but that takes ages, of course. That takes ages, and it's not even possible on a single processor. Yeah, I mean, on the other hand, we have, of course, calculated the average already.
Yes, no.
You're using the average file.
It takes the var file, it computes for each var file the fluxes, and then it takes the horizontal average and the.
But you're not doing this within the active procedure, or what? You're not doing it within the active procedure.
No, it's my home process.
Please, sir, can we make it so that instead of compiling a little executable, it compiles a module for the pencil code, so you can do this online?
Yes, of course. Yeah, you can do that online. Exactly.
So at the minute we don't have a way of doing this, but we've been thinking about doing. There are certain diagnostics that really you don't want to save all of the bar files for 500 things, just so you can have some particular output.
That's right.
If you have a module that you can.
Yeah. And then let me show you.
You know what I mean, right?
I'm not sure.
So, for example, also one of the diagnostics, the Fourier diagnostic, which is very important in my case, the depth and the frequency, and you can show the peak corresponding to internal waves. Convection zone, radiative zone. Here, the peak corresponding to the propagation of waves. Okay, and also the convergence of the simulation. So here it's the horizontal wave number, and here the power spectrum, and you see that the simulation is well converged. Okay, and then for the problem with Axel, an oscillation package, which computes the equilibrium model, the eigenmode of the box using a Fortran solver, okay, and then projection onto the mode, base mode, that's our method, and finally the sum of every mode compared to the total kinetic energy of the simulation, and here it shows that. For example, K equals 1 mode, all modes contribute to 2% of the total kinetic energy embedded in the box. So, that's what I would like to show you, that I plan to, in fact, to add more things to this interface, for example, magnetics.
Fantastic.
Yeah, and one good thing in this interface, you know that when we read a var file, one problem is that we need to each time launch PC var content.
No, you must not. You must use PC read var. This is the whole point of having PC read var. The only code that should ever touch a var file is one IDL routine. Then if the structure of a var file changes, only one program is edited. Otherwise you end up with where everything is implemented 10 times, right?
When you read a var file,
you mean.
but now I read the grid one time, and then this one, var content, PC var content, data, top gear, files, etc. And now I replace that by a setup. And in the setup file, I read only one time this one, the grid and the var content, and after that, the var file, I only read the var file, not the PC var content and so on. And then it go very fast now.
Ah, right.
You see? Because the setup, when I click on setup, in fact, I just read everything in this case here, setup of the simulation, and everything is stored in some common. And after that, when I read the var file, I read just the binary file, and not.
I'll just write a cache so you can cache the var content information.
So I was almost about to say, but these are things which only one person would ever use. I mean, I couldn't imagine any of you. I mean, could you imagine Natalia being?
Yes, but the thing.
But in fact, there is a process.
A lot of the online diagnostics. If the code is nice in general and it's something you can add to, the problem is that there's a certain overhead in creating the first interface.
Yeah.
Once the general code's there, it's very easy to add buttons and add things.
What I would like to do, I would like to see the interface and having some magnetic.
I'm looking to interface this to visit, for example. So I've got this 3D interactive visualization.
Exactly, we can do that.
Put that in there, right?
Just some general interface.
So, for example,
after that, people can get a specific problem.
But actually, specifically, I think I could actually use it just as it is. Because I would like to know the oscillation, the P-mode frequencies of my box.
Of course, then you can use that.
But have you even checked this in?
Yes, the P-mode are in the interface. Huh?
So this thing is checked in, you say. How do you invoke this? And it works on...
Here, also, you can get also the P-mode, G and P.
Yes.
And you get also the acoustic mode
Okay.
for K equal to 0 to K equal to 3 or 5, what you want. But you can project on that mode also.
Okay, so how can you tell me what to do then? I mean...
Yes, of course.
But not yet, or what?
Now, what I would like is just to see some problem you have in your
I do. I have a problem. I can show you.
Yeah.
Okay, let's do it after the break, maybe.
And I think it's ideal. It's
Cache. There's a cache built into the PC read var content now. You don't need to do that trick you use, does it? All you have to do is when you call PC read var, you just say var content equals var content, and the first time it will fill that variable. But as long as you pass it the same variable next time, it's already ready.
Okay, so but it's not the main point of.
No, but cool.
Yeah, the main point is that I think it's a good idea to have some widget for some given problem. So a guy which is very new in the pencil code can plot very easily the entropy, the magnetic field, or something, some very rapid diagnostic using the widget, and with no .r times some kind of PC underscore routine that actually we have, because with that we don't need a manual for the graphics.
That's right.
I think it's a nice addition, but I have to say it's a nice addition. But the worry would be that, of course, by what you're suggesting, but then we don't need these PC reads thing. But I think you do still need the general routines that are well documented.
Exactly.
Because while, as Axel says, this, there are 100 other things that everybody might want to do.
But we can do this.
Yeah, exactly. I mean, you could never enumerate all the possibilities. So the best thing is to have the routines that are general.
Yeah, but we can also have some very simple interface with a first diagnostic output. Some printing also. Each snapshot is printed automatically, postgrade form, and then.
Is it checked in? Is it?
Yeah.
Or is it?
No, I didn't. For the moment, it's not checking.
Why not?
Because I was the only guy who used that. So,
but I mean,
create a directory under IDL.
In 5 minutes, I will use it. Yeah. Look. Is that all you
This is what happens when you check something new in, and like 20 minutes later you get an email from Axel going, so how does this work? Oh yeah, 30 minutes later, there's a paper.
Yes, another thing also before finishing. It's why I implement the new boundary condition. And I would like to show you just why.
Maybe you can make the pencil code such that even Patrick can use it then.
Again, that's another worry as well. That you have to be very careful with these automatic diagnostics. That things that produce pretty pictures are very good at convincing people they've done the right thing. You know what I mean? If you.
And what is the bad thing about it?
Hey?
And what is the bad thing about it?
It's use, right? You end up with this use situation where people go, oh yes, it works very well because it produces a pretty picture. That doesn't necessarily mean the pretty picture's right.
Yeah, but
you've got to be careful, right?
I would like just to show you why in the code now we have a hydrostatic equilibrium boundary condition. It is because when I would like to studize the oscillation generated by an entropy bubble. And in this case, using the CT boundary condition, it's an isothermal atmosphere, okay? And at the beginning, I put a bubble of entropy there. The bubble go down here and begin to oscillate. Okay? And we have an internal wave field, which is generated. And I need to get constant temperature here and here, okay?
What does it mean color coding then? What does it mean color coding?
That's the velocity field, and you see the velocity field.
Color code.
The color.
Yeah.
It's entropy control. Okay. And using the CT boundary condition is not correct, because in this case the entropy gradient at the bottom and top of the zone was incorrect. And then now, for dealing with that kind of problem, the hydrostatic boundary condition is better.
Is the velocity vector scaled with respect to the maximum length at every given time, rather than a constant value?
The velocity?
Yeah. What's the length of the vector? Is it?
It's a given length. I impose a given length.
So it's an absolute thing, yeah?
Yes, absolute thing, yeah.
Because it looks so weird. Is that right? It looks so weird, as if you have rescaled it with respect to the maximum at every given time, which is changing. No?
Brilliant.
No, normally because in this simulation the viscosity is very small.
What's the aspect ratio and the horizontal?
Yeah, the aspect ratio is not very. It's 4.
Yes.
And the viscosity is very small, and then the velocity tends to zero, very small, very.
And it's 2D, by the way, right?
Yeah.
I mean, in 2D, the horizontal extent will be much larger than in reality.
Yeah.
Because of the.
And then that's a very simple problem, but this problem has shown that we had a problem with boundary conditions in the code. So that's useful. And then this sample now is this problem is a sample to this directory of the
Entropy bubble, right? Entropy bubble.
Yes, entropy bubbles. Now I had a bubble directory in the
Are
sample.
you solving radiative transfer?
No. It's just you have just hydro, so entropy, density, and viscosity.
So that's a summary.
No magnetic field.
No magnetic
It's just an hydrodynamic problem.
I mean, it's a problem that you can solve analytically. That's why it's done this one.
Yes. This problem can be solved. The oscillation are analytic, and then that one, this atmosphere we check. We take this atmosphere of Jackson in a paper to validate our method, projection method. And I did once again this problem with a student of mine in Toulouse, because we are interested in the acoustic mode now, not simply internal wave, because the bubble is not in hydrostatic equilibrium at the beginning now. And then we generate acoustic modes. And then the question is, what is the relation between the acoustic and gravity spectrum compared to the size of the bubble, for example?
So, the acoustic waves damp out here?
No, here it's just internal waves.
Oh, I see, there is no...
Yeah, just internal wave because the bubble is in hydrostatic equilibrium.
Okay.
As a beginning.
Are you saying there's exactly 0 P modes?
No, here just G modes.
I mean, are you saying P modes are exactly 0?
Not exactly 0, but very small compared to G modes. If you make the projection and you use the ratio between kinetic energy embedded in G mode compared to total kinetic energy, it's around 98%, and just 1 or 2% are acoustic modes.
Yes, okay, right. Yeah. Okay. Anything else?
What's wrong with the plotting between that? It looks like it's doing the white plot black in the top half, but it wasn't doing it in the bottom. Can you see that?
No.
What?
There's something wrong with the plotting. You know, you plot a white arrow, then you plot a black arrow, where the white arrow is slightly bigger, so that whatever colour background you see it.
Yeah.
It was doing it in the top where it was light, but at the bottom you couldn't see.
Yeah.
Just noticed, I don't know if that's your routine or Wolfgang's probably developed after a while.
And then last time I discussed with you about the cloud preprocessing, and I can show you what I mean. See, that's the file. It's the AXI file where we put the whole equation.
Very cool.
So we put the primary variable, which is the radius. The secondary variable, it's the order of the spherical harmonics. Okay. We put some definitions which are global in the code. Some input data that we can that one need to start the run. So the Chebyshev grid resolution and the angular spherical harmonic grid resolution. Okay, and then some problem related to the star. And then the variables. So the toroidal field, the radial field, the velocity, and the temperature, and the index, the spherical harmonic index between L min to L max, and because we have Coriolis force, the spherical harmonics are coupled together with L plus minus 1. And then if the toroidal field begins to L mean, it means that the radial field begins to L mean plus 1. And then we put the equation for each variable. A symbolic form. For example, here the field is for the code is for derivative. So no derivative, the first and the second derivative.
Very cool.
It's a left part. So this one is simply half c equal to lambda bc. And then we fill, so we get the left hand side and equal to the right hand side. Okay? So we do that for the three variables. We give the boundary condition for each variable. The interface condition if we have two grids, for example, two check grid, and we give the interface condition between the two grids. So normally it's just simply the value of the function itself and also the first derivative, for example. And the order of the variable to build the matrices here, the eigenvector can be WVT or WTV. It's better sometimes to interchange to get smaller matrices. Okay? And the order of equation, how we write the matrix here, so we can put XV, XWV, T or interchange till for some problem side. And after that, we did that. LSD.pl X. And the third preprocessing, we have the original file, and we get the good file.
But a brilliant demonstration of abstraction, right?
Yeah. And after that, we make an extract.
So which one
That
did
was
you...
useless, though, right?
Not anything like
No,
that.
not that level. But the idea is there that you start with a template and you run, what's it called? Editor.
Oh, it doesn't really use that anymore.
No, I mean old
Old
schools.
school version.
Yeah, this is what old schools used to do.
Yeah.
You used to rewrite the code when you actually changed the parameters.
In the basic code, actually, we have the problem of dummy subroutine. No magnetic, no entropy, no, and so on.
Imagine this,
It can
this would be one very good
this
solution.
kind of stuff.
This would be a very good solution for that.
Ah, yeah, very good.
Can you show us how the code looks like for this
But
example?
2009, which was very
I
complicated.
mean, like the line...
Show us one like
the subroutine.
like one that evaluates
So-
psi or something, right?
So this is a third program. You see that's very complicated. So actually we have more than 2009. And
you actually write your program as a Perl program. So
Yeah.
you don't have a template. Which
yes, of course. For example,
Oh, sorry, yes, you showed me the Perl. Right, so that's what the
MD5.ft. So that's a template of the.
This is what we want to see, yes.
And you see, start parameters, end parameters, and the Perl preprocessor we write here.
We have some crude versions of this.
Yeah.
In that, so for example, we do it slightly differently. Instead of putting stuff in line, we create a new file. So if
Okay.
you look at, for example, C-program docking, you can have modules. You can write stuff in the top of a module. You know, this C-program find thing, and the Perl thing goes and gets it, finds it, and then builds an appropriate C-program docking.
Yeah.
So we have a crude version of it. Nothing as brilliant as that, which actually
No,
handles the
yeah.
equations, but it's kind of.
That's certainly one. You see, for example, start my RHS and my RHS. Here, the Perl preprocessor we write the right hand side of the equation.
Appropriately formatted.
Yeah.
Very clever.
So I think that's one good idea. So certainly a very big stuff. It's not so easy to implement, but it's maybe one way to. Maybe we can mix. For example, with Ocus code, I did that. I begin to do that. For example, to have 2D program compared to 3D, because Ocus code by default it's 3D. And in 2D, for example, for the isothermal bubble oscillation, I put just in the code some paragraph. Each I'm in 2D isothermal or 3D polytropic. So is that possible to do that?
I mean, that's a slightly different thing, of course. There's a question of should we implement our very own Fortran preprocessor? Because, I mean, in C you have a preprocessor. So I can say if hash defined but, and there are many objections to it and whatever else, and things, I mean, it's been discussed many times. Some compilers have a Fortran preprocessor, but they're all different.
But there's also the C preprocessor works on Fortran. That's the way it's used for us now.
Indeed. It's a little bit.
Yeah. But it's ugly and nuts.
It's ugly and nuts. Exactly, the syntax looks out of place somehow.
Yeah. It's very hard to figure out what the hell is going on.
So this is quite a nice way of saying, actually, we don't want a very general preprocessor. There are just some features of a preprocessor we want. Let's have our own explicit notation and our own explicit preprocessor. And if Perl is an acceptable dependency, which Wolfgang keeps insisting it is, of course. I mean, you have to have Perl to run the pencil code.
Yep.
You cannot run. Running it in Windows was quite fun.
You ran it in Windows?
Yeah, we tried running the pencil code with G-Fortran in Windows, right? But the hard bit is you have to go through, and all of the stuff that Perl does, you have to do by hand.
You can't do Perl doesn't run on Windows?
Unfortunately, the Perl stuff has been written so that Unix can't be used. So there's some problems with those sorts of things. But yeah, so there you go. We've not done much. We managed to get conslab working and things. That was the. Can you run the pencil code in Windows? Yes.
Yes. You see, for example, in Orcus code, what I did is simply I put in exactly the same stuff, but a big F, okay, and you just put some sentence like if def isotherm, then I get.
And you then implemented the Perl program to do that.
And only.
You made a Perl program to do that.
Yeah.
Well, the interesting thing is what Jeff's saying, and what I've tried doing as well, that if you just took that file now, if you did cpp space minus D capital D isotherm, and you run the C++ program.
Exactly.
Yeah.
And here I just put a conf from there, something like makefile.local.
Yeah.
I put define.
Yeah.
So we can do the same, exactly the same.
I agree 100%. There are many people who object to preprocessor directives because it makes things ugly and messy. But like all of these things, I think everything should be used in moderation. Everything has a correct purpose. Some people see this preprocessor and then they say, "Oh, I'm actually going to make this." You end up using it to write your code, but just as you shouldn't not do something because you can't do it in one case doesn't mean that because you can do something you should do it in all cases. That issue happens both ways in code.
Yeah.
But that's really neat. Yeah. I agree that we should probably use that a little bit.
Right. Now the compilation sometimes.
Will you write an email to Wolfgang suggesting that?
Yeah.
I mean,
For example, that's
in that case, we did end up with a code which was very difficult to read.
Yeah.
And we have so many if constructs.
Yeah, it's just impossible. Right?
And then you really don't know. And then you try to explain it to the newcomer, right?
Yeah, but actually,
becomes very
in the
important.
Orcus code, I did that with HIF and HIF and so on, but you can do that also with Perl, which is, you have the Perl program outside, and you put everything in one Perl program, and the Perl program puts the good paragraph.
So here's what the pencil code does that's really neat. The switchable modules, and the reason all of this private thing is important, is that you could write all possible ways of evaluating density. So let's imagine we did log density and density. You could write this in one Fortran program, and then you could have a load of hash defines, so this density module is pre-processed. Right? And that way, because what you do require is you require the interface to your, the things that this module provides must be standard. So within the source code it must be self-consistent. But the other way of doing it is you take the two things and you pull them apart, and you don't use hash defines, but then you have the problem that you have to guarantee that the interface to these two things is identical. Right, so this is where you have to do data hiding. So what we have in the pencil code, if we had this, we'd have both methods, and we could always use the correct one for the correct task.
Yeah, the good point.
The minute we only have the private thing, which isn't properly implemented, and we can use
the good point is that.
I mean, this is sort of the extreme, right?
Yeah, I mean it's horrible, right? This is where switchable modules. So 90% of that happens as
This is okay. That's just variables. That's the definition, declareless. And you can see you change, you add these extra reals if you have isothermal.
Exactly.
If you don't have isothermal, rather you have to put on the density and that's bad. That's one. But what's worse is this. This will make your head explode.
Lecture guys aren't talking about that.
Can you put this up?
Is Wolf done?
Yes. Good one.
So just as an example, could you?
Yeah, it's funny.
Maybe we should thank Boris first of all.
Yesterday you did something. You said something which is.